The very present morning to one Dr. Present. This is Dr. K.S.Rangasamy, Professor, Department of Mechanical Engineering, K.S.Rangasamy College of Technology. Today I am going to talk about vibration. This comes in the Dynamic Submission subject code 50ME502. So, introduction to vibration. When elastic bodies such as spring, a beam, and a shaft are displaced from the equilibrium position by the application of external forces and then released, they execute a vibration. This is due to the reason that when a body is displaced, the internal forces in the form of elastic or strain energy are present in the body. At the release, these forces bring the body to its original position. When the body reaches the equilibrium position, the whole of the elastic or the strain energy, which is converted into kinetic energy, due to which it continues to move in the opposite direction. The whole of the kinetic energy is converted into strain energy, due to which the body again returns to its original position. In this way, the vibratory motion is repeated indefinitely. The terms used in vibration, period of vibration, there's a time interval between the motion and repeated itself. The period of vibration is usually expressed in seconds. Cycle, it is the motion completed during one time period. Frequency, it is the number of cycles described in 1 second. It is also expressed in terms of hertz. So, which is equal to 1 cycle per second. Types of motion. There are three types of vibratory motions available. One is free vibration, second one is forced vibration, third one is damped vibration. So, the free vibration, when no external force acts on the body after giving an initial displacement, then the body is said to be under free or natural vibration. The frequency of the free vibration is called free or natural frequency. Example, the pendulum clock, where we are giving initial force to vibrate from its initial position. So once it is given, then it is repeated. That is called free vibration. Forced vibration. When the vibratory body vibrates under the influence of external force, then the body is said to be under forced vibration. The external force applied to the body is a periodic disturbing force created by unbalance. The vibration have the same frequency as applied force. When the frequency is the external force is same as that of the natural vibration, resonance shift is. So here the example of fan blade or a fan makes certain sound, that is because of bearing has gone or some unbalanced force. So you are continuously rotating the fan with the help of external current. So that is why that vibration repeats. So that is example of forced vibration. Third one is damped vibration. When there is a reduction in amplitude over every cycle of vibration, the motion is said to be damped vibration. This is due to the fact that certain amount of energy possessed by the vibrating system is always dissipated over overcoming frictional resistance to the motion. The example of damped vibration, the rubber bush which is provided in the mixer, grinder, or any of the rotating object wherein we have placed. Say example, in lathe bed also we are providing bushes, rubber bushes, while installing the lathe or milling machine or whatever it is. Next, types of free vibration. The following three types of free vibration are important from the subject point. One is longitudinal vibration, second one is transverse vibration, third one is torsional vibration. Concerning a weight which is attached in the shaft, one end is fixed, another end is the weight W is attached. This is used for all the category of experiments. So diagram A shows for long-term vibration where the vibrating motion takes place along the shaft. That means the first you can see the three different position of the shaft. The blue line shows the initial position of the shaft. The pink line shows the when external force acted that elongates, and when the external force released and it goes back, and like that it vibrates to and fro, so that the pink line is changing from C to A to C via B. So this is an example of long-term vibration where uh, the molecules move along the axis of the shaft. Second one is transverse vibration. The diagram B shows the example of transverse vibration. The line blue position B shows the neutral position, A the left extreme position, C shows the right extreme position. When external force acts, if the vibration takes perpendicular to the line of action, then that vibration is known as what do you call that? Transverse vibration. So the third one is torsional vibration. So here you can see that again the blue line shows the initial position, and it's otherwise called in the diagram capital B, and the A and C are the uh, motions of the disk with respect to type of whether we have to do clockwise rotation or counterclockwise rotation. So based on it, if you any twisting moment to this, then it starts to move from B to C or B to A. It depends upon in which direction it is applied. So beyond which it won't go. So because of that, it comes to origin towards equilibrium position, and because of its having kinetic energy, it goes beyond B and reaches C. So once after reaching the C, again it returns to tries to go to position B, and because of the kinetic energy it goes beyond it and reaches A. So then that cycle is repeated. Then this type of vibration is known as torsional vibration. Now the natural frequency of free long-term vibration. The natural frequency of free long-term vibration may be determined by the following three methods. The first method is equilibrium method, where you consider a constraint or the spring, which is one end of the spring is fixed, another end of the spring is really here. So its weight is negligible, and then unstrained position is shown in the figure. We have three positions of the spring position. The first one is without strain. That means it is not attached with any load. The diagram B shows the weight W or mass M is attached to the free end of the spring. So because of that, it gets deflected. That deflection is known as static deflection. That is denoted by delta, which is shown in the diagram. The third diagram shows the when external force act on the W, so it tries to goes down. That is shown in the form of pink dotted line. So that you can see that how it is moving. So once after reaching the bottommost position, that is X is the displacement given to the body by the external force in terms of movement. Now there are certain things or certain terminologies you have to know it while going with the vibration of springs. Let S be the stiffness of the spring. So stiffness is amount of load required to produce unit deflection is known as stiffness. So it is usually expressed in terms of Newton per meter. The small m is the mass of the body suspended from the constraint in kg. Capital W is the weight of the body in newtons. It is expressed, it's mathematically written as m. Where delta is a static deflection of the spring in meters due to the weight W. It's Newton. Its deflection is unit is mm, and x is the displacement given to the body by the external force in meters. Now, in the equilibrium position, as shown in the figure D, the gravitational pull W equal to mg is balanced by the force, spring force, which is equal to W equal to S into delta. Since the mass is displaced from its equilibrium position by a distance x, as shown in figure C, then released, therefore, after time d, restoring force W equal to, you can see that from this equation. So, alternating force equal to accelerating force is equal to mass into acceleration, which is equal to m into d square x by dt square. Now, the equation 1 equal to minus sx, that restoring force. Equation 2, accelerating force is equal to m into d square x by dt square. So, the equating the equations 1 and 2, then equation of motion of the body m after time t second, m into d square x by dt square equal to minus s into x. So, this can be written as that the other side can be brought this side and equating to 0. So, m into d square x by dt square plus s into x equal to 0. So, the entire equation is divided by m. So, you will get d square x by dt square plus s by m into x equal to 0. We know that the fundamental equation of simple harmonic motion, d square x by dt square plus omega square into x equal to 0. This is equation number 4. The earlier equation number 3. Now, comparing equation 3 and 4, you will get omega is equal to s by m, or time period Tp is equal to 2 by divided by omega equal to 2 into pi into root m by s. Now, and natural frequency ft is equal to 1 by time period is equal to 1 by 2 pi into s by m equal to 1 by 2 pi into g by delta. Taking the values of g as 9.81 meter per second square and delta in terms of meter, when you substitute these values, then the Fn is equal to 1 by 2 pi into root of 9.81 divided by delta. So, after putting the value pi equal to 3.14 in that equation and cancelling the numerator and denominator, you will get 0.4985 divided by root delta in terms in hertz. The value of the static deflection delta may be found out from the given conditions of the problem. For long-term vibration, it may be obtained by the relation stress by strain equal to H minus. This is a common equation where the stress is expressed in terms of load by area and the strain is equal to change in length by original length. So, using that, we can express. So, or else W by A into L by delta equal to E. We are interested to find delta. So, the delta can be calculated using equal to W into L divided by E into A, where delta is the static deflection or the extension or the compression of the constraint. W equal to load attached to the free end of the constraint. L equal to length of the constraint. E is equal to Young's modulus of the constraint. A is equal to cross-section area of the constraint. Thus, delta can be found out using different methods. So, that is by what we call it, from standard material point of view, you have different types of beam, like single supported beam, cantilever beam, overhanging beam, fixed beam, like that. You have many types of beam. For that, you have a set of equations, or already the equation has derived in standard material or static deflection. So, either you can use the equation or you can find the delta experimentally from the setup. Then that delta value can be used to find the frequency of the system. So that helps.